Hello everybody, and welcome to my talk, in which I will give you some insights and overview about the whole advanced recycling topic. So for some it might be some kind of a black box, which I really want to resolve with this talk. So, and also for the first time, I will give a larger audience some first insights into the European input and output capacities, and also insights about how the capacities will evolve in the near and far future. So with this, I hope to give you a better overview about the status quo, so where we stand and where we go with recycling, specifically with plastics recycling. So before I start my talk, so maybe a few words about NOVA, especially for those who might not know us. So NOVA Institute is located in Germany, in the wonderful city Hürth, nearby Cologne. We were founded in 1994, and meanwhile we established a multidisciplinary and international team of nearly 50 scientists, and together we are offering our customers science-based consultancy around the whole topic renewable carbon, which can be bio-based, CO2-based, and based on recycling. And with that, we support the chemicals and materials industry by their transition to renewable carbon away from fossil carbon feedstocks. So let's directly start with this graphic to introduce you the advanced recycling topic. So if you have a look on this figure, you quickly realize that with advanced recycling, we have a large toolbox of different technologies that are able to address different kinds of plastics wastes and to convert these plastics wastes into products that can be later reintroduced along the whole value chain of plastics. So we not only have material recycling, which is a physical process based on dissolution. You have also chemical recycling, and this can also be subcategorized on its basic working principles, so into depolymerization and conversion. Depolymerization technologies would be enzymolysis, so it's a biochemical process, but we have also chemical processes, including solvolysis by utilizing chemical solvents. And then you have also thermochemical processes in which you utilize thermal depolymerization. So, and for the conversion technologies, you have, again, thermochemical processes, including pyrolysis and gasification, but also incineration if you consider larger recycling loops, if you consider carbon capture and utilization. So before I dig deeper into the recycling technologies, let's start with some statistics, and let's analyze a bit the status quo about packaging recycling and how the packaging waste is composed, and where we stand. So in Europe, annually 84 million tons of packaging waste is generated. So, and the majority of this packaging waste is composed of paper and cardboard, so 34 million tons, and 16 million tons of plastic waste. So looking at the paper and cardboard recyclings currently, so last time analyzed in 2020, we had a recycling rate for paper and cardboard of 72%. And if you closely look at the numbers on the left-hand side, you see there's a more detailed bar graph, which shows you recycling rates for different kind of paper packaging. And here you directly see, okay, non-hybrid mono paper material has the highest recycling rate of 82%, but hybrid packaging, so multi-layer material, which you usually find in beverage cartons. You have different kind of materials in there, including aluminum, but also plastics, and together with paper. And these materials are really difficult to recycle, and therefore you have here much lower recycling rates. So, but if we look at plastics at a whole, so here are some additional numbers about plastics. So in Europe, annually 30 million tons of plastics waste are generated. So this includes plastic packaging, but also other categories. And from this 30 million tons of plastic waste, 29.5 million tons are collected. So this is definitely the majority, but still 0.5 million tons is leaked into the environment. From the collected plastic waste, 42% is going into energy recovery, so incineration and energy recovery. 35% is going into recycling and 23% is going into landfill. So with this, more than 50% of the collected plastic waste is treated with the least preferable option according the waste hierarchy. So there's much more room for improvement to increase the recycling numbers and to decrease the numbers for landfill and energy recovery. So, yeah, these slides, I wanted to show you the ambitions of the European Union. I think that Anna already gave a very detailed insight into this. So not really new numbers for you, but to make it quick. So the European Union has established quite ambitious plans for the recycling. So here we have, first of all, the recycling quotas, which needs to be achieved until 2030. So already mentioned 70% for all packaging materials and 55% for plastics, as well as 85% for paper and cardboard. Then we have the mandatory recycled content. So this is currently discussed in the revision for the Packaging and Packaging Waste Directive. So lastly discussed was a mandatory recycled content, which needs to be achieved until 2030. So, and here we are talking about 30% mandatory recycled content of PET in contact-sensitive packaging, and 10% for other plastics in contact-sensitive packaging. The European Green Deal as an overall concept goes a bit further. So here it was communicated that until 2030, all packaging and packaging materials should be recyclable or reusable. So, and as a long-term goal, until 2050, the European Union will be climate neutral. The question now is, how do we achieve all these targets? So in general, we have 5 options available, which I want to discuss in the next 2 slides with you. So first of all, we have the prevention of plastics. So by replacing plastics with other materials. So this is economically and ecologically meaningful for only a few applications. So you cannot simply replace plastics with other materials because very often you have no existent or very limited alternatives to these materials. So the reason is plastics are have a superior density to strength ratio. So we have very strong and lightweight materials. So it's not easy to replace such kind of materials. Plastics can be easily be formed and reshaped. So if you're looking at thermoplastics, so they have very superior processing properties. You can form and reshape them only by the application of heat. So this is another advantage of plastics. And then you have a huge sector of specialty and high performance materials with very tailored properties. And if you look at the sustainability criteria, plastics has often the better performance. So you know the discussions comparing plastic bottles with glass bottles, and yeah, that plastic bottles are often or are always much lighter than the glass bottles, and yeah, so for a lot of applications, yeah, plastics have also better sustainability criteria. Then we come to the options reduce and reuse. So if we're talking about reducing plastics, this is possible with intelligent product design. So with that, it's possible to introduce less plastics into the cycle. So this has a certain potential. This means in turn less generated plastics waste. And if we talk about reuse, this is also an option. I think this could be a bit limited because yeah, reuse itself cannot fully prevent the generation of waste. With reuse, we are talking more or less about a delayed waste generation, so also relatively limited. Then we are coming to alternative feedstocks based on renewable carbon, so can be bio-based or CO2-based materials. Feedstocks, and yeah, this prevents the introduction of fossil carbon into the cycle. So in turn, it helps to achieve the long-term goals of the European Union to be climate neutral. But again, this is not a direct solution for wastes. With this, we come to recycling. So it's the only option to largely prevent landfill and incineration. It keeps the plastics in loops. Of course, also there are some limitations, so you are not able to keep always 100% in the loop. So of course, with each recycling step, you have some losses, which you in turn need to replace with other renewable feedstocks. So with this picture, so let's simply imagine a life of a polymer without recycling. So without recycling, the life of a polymer would be really linear. We have, yeah, with landfill and incineration and energy recovery, only very limited options available that are always coupled either with greenhouse gas emissions, but also environmental pollution. So, but if we now consider in a complementary or integrated approach all recycling technologies in the life of a polymer, you realize that yeah, the life of a polymer can be really, really circular. And we have various options available that help to reduce not only the greenhouse gas emissions, but also the environmental pollution. So, and with this overview, this is very simplified. I want to show you the pros and cons of mechanical recycling on the left side, but also chemical and physical recycling on the right side, which we call advanced recycling. So first of all, mechanical recycling has some pros. So it's characterized by its simplicity, and it's well established over the years, so a well-developed technology. However, we have some limitations here. So first of all, we are only limited to thermoplastics. So other components like composites or rubber or used tires cannot be easily mechanically recycled. So this is the first limitation. The next limitation would be we have a need for more or less pure fractions. So for the primary recycling, which is the pre-consumer recycling, this should be not a problem because primary recycling is, yeah, or the pre-consumer waste is characterized by its purity. It's very homogeneous. There are no contaminations in there, and often we perfectly know its composition. So perfect conditions for mechanical recycling. But if we talk about post-consumer recycling, so the secondary recycling, then we are approaching a very critical waste stream because here the waste stream could be very heterogeneous. it could be heavily contaminated, and it could also have an unknown composition. So it's really necessary to analyze this waste stream and to sort it. And there's a lot of pre-treatment necessary in order to address it with mechanical recycling. So another point is contaminations cannot be removed from the process. And with mechanical recycling, you have a loss of the molecular weight of the polymer. So I left here some numbers for PET recycling. So if we repeat the mechanical PET recycling 3 times, you have a loss of molecular weight of 56%. So the polymer's length will be shortened over time. So this is, means also decreasing quality. Here, in case of PET, after 3 cycles, we have a significant loss of impact strength and tensile strength. So looking now on the chemical and physical recycling side, so here on the pro side, we are not limited to thermoplastics only, so we are also able to address composite material and rubber, for instance. We have no need for pure fractions. So of course, there are some requirements for the input stream, but in general, we could say that the chemical and physical recycling processes are more robust and don't require that much sorting and that pure fractions like it's the case for mechanical recycling. Furthermore, we are able to remove contaminations, so flame retardants or can be removed from the process. This is another pro side. So with chemical and physical recycling, you should also be able to produce virgin-like quality, virgin material, which is also food contact approved. So on the cons side, we have that chemical and physical recycling is relatively complex. Because these processes are not well established, we are currently lacking large-scale units. And with this, we also have some difficulties to prove sustainability. So let's go through all the recycling technologies, beginning with the dissolution. So dissolution is a physical recycling process. With this, you can dissolve a target polymer in a suitable solvent. All the other components of plastics will not go into solution. So other components could be non-targeted polymers, but also pigments, fillers, and other contaminations. So once the target polymer is dissolved, it can be cleaned from the other components of plastics, for instance, via filtration. Then you could add an anti-solvent, which initiates the precipitation of the targeted polymer. And then you can wash the target polymer. And in the end of the process, you have the purified target polymer. So this process has, again, some advantages. So it's characterized by its selectivity. So you can address very specific polymers. And with this, you are able to address even mixed and multi-layer material. Another advantage is that you can directly use the product, so the polymer, so no polymerization is necessary after the process. And toxic substances can be removed from the process. On the disadvantage side, there are some requirements on the composition of the input material. So of course, in order to have an economically and ecologically meaningful process, you need a certain amount of your target polymer. With this process, you are limited only to thermoplastics, and the purification of solvents after the process is still necessary. Worldwide, we identified 8 technology providers, and the plant with the highest capacity has 8,000 tons per annum. Now we're coming to the next process based on solvents. It's the solvolysis. It's a chemical recycling process. In this process, you are able to depolymerize a polymer with a suitable solvent in its building units. This could be monomers, dimers, trimers, oligomers, what else. And depending on the utilized solvent, you have different names for the solvolysis process. So you could have alcoholysis. For instance, if you utilize methanol, you could have the methanolysis. You could also have the hydrolysis, but also the ammonolysis. So after this depolymerization step and purification step of the building units is necessary, and this is very critical. So in the end, you would like to have a very pure fraction of your building units before you go into repolymerization. And here we are talking about very high purities which are needed. So usually over 98%. And this is a very critical step, and usually you do this with distillation. Similar to the dissolution, we have some advantages. So again, we have the selectivity and possibility to address mixed and multi-layer material, and you are able to remove contaminations. Again, on the disadvantage side, you have certain requirements on the composition of the input material, especially if we talk about the polymer of interest. Again, you need to purify the solvents after the process, it's necessary to have an additional process after the depolymerization. So you need to repolymerize your building units. So an additional process is necessary, which makes it more complicated. And another limitation here is polyolefins, so polyethylene and polypropylene, as well as polystyrene, cannot go into the solvolysis. Worldwide, we have identified 22 technology providers with a maximum capacity of 10,800 tons per annum. Now we are coming to the first thermochemical process, the pyrolysis. With this process, you are able to address highly mixed polyolefin wastes in presence of heat and absence of oxygen. You convert with pyrolysis the feedstock into solids, gases, and liquids. So you could obtain different products, which can be char, syngas, different kind of liquids, so pyrolysis oil, monomers, naphtha, diesel, so a wide range of different liquid products. Then, of course, waxes and ash. So on the advantage side, we have a wide range of input materials can be accepted. So even a co-pyrolysis is possible with biomass to a certain extent. You have a large spectrum of obtained products, as you see here in the figure, but this is at the same time a disadvantage. So if you only want to obtain naphtha, you always have to cope with the other products, and you need meaningful applications for these products. Of course, you can adapt your process and you can increase the yield of certain kind of products, but there are some limitations, and you will always obtain different kind of products. Another disadvantage is the high energy demand, possible emission of pollutants. Furthermore, depending on the end application you are aiming for, the products often needs to be further processed and upgraded. So if we talked about naphtha, you need some further processing in order to be able to direct your naphtha fraction into the steam cracker. We have here in this process a low tolerance of PVC, but I think this is also true for mechanical recycling and many other processes. Worldwide, we identified 62 technology providers with a maximum input capacity of 30,000 tons for one technology. Now we're coming to the last thermochemical process, the gasification. So here you can address even a feedstock with an even more heterogeneity, so you're able to process this feedstock into syngas in presence of even more heat than in pyrolysis, and in presence of oxygen. So the process can be very robust regarding the input material. We have downstream various applications for the produced syngas, and contaminations can be removed. But here on the disadvantage side, we have an even higher energy demand to the very high temperatures and pressures that are generated in this process and also necessary. Especially for plastics here, another limitation is higher tar contents could be found in the product. So here in this case, if you want to utilize your syngas in turbines or engines, and maybe also in other applications, further processing and cleaning is necessary. So worldwide, we identified 10 technology providers with a maximum capacity of 100,000 tons per annum. So the process with the largest scale here, which I'm showing you. Now we come to the enzymolysis. So enzymolysis is describing the depolymerization of a polymer via biocatalyst, so into its building units. The process can be very, very specific and can be done under relatively mild conditions in comparison to the other technologies. So for instance, at room temperature and atmospheric pressure. And however, the process is rarely developed at the moment. So it's only at a lab scale and with a relatively slow turnover. And therefore, we at the moment only identified one commercial technology provider with a very low scale. So so we had a look now on the technologies and their providers. So let's make a small excursion through the installed capacities in Europe. So we had a very detailed screening for the plants which were installed worldwide. And we also have analyzed which kind of plants are installed in Europe. And with this evaluation, we found that currently 66 advanced recycling plants are currently installed in Europe. So worldwide are 228 plants installed. The majority of plants can be found in Germany and the Netherlands, followed by UK and Spain. So, and the total input capacity in Europe is currently 358 kilotons per annum. Worldwide, we have 1,477 kilotons per annum. And looking at the specific input capacities by technology, as well as their specific product outputs, we also gained some very, very interesting insights. So on the left-hand side, you see the input capacity divided by technology. Here you see the majority at the moment from the 358 kilotons is addressed with pyrolysis. And so it's 275 kilotons, followed by solvolysis, so with 69 kilotons. And a much smaller waste fraction is currently addressed with dissolution, so physical recycling, and even lower with enzymolysis and gasification. So gasification in the worldwide comparison, gasification will have a larger share. So, but in Europe, we don't have at the moment large-scale commercial plants. And looking now on the output side, so we are currently obtaining 271 kilotons per annum of products. Products could be divided into polymers, which are coming from the dissolution. Then we have the monomers, which are mainly coming from the solvolysis. Then we have naphtha, SVC, so secondary valuable chemicals, and fuels and energy, which is coming from pyrolysis and gasification. You see that the major share of products is represented by secondary valuable chemicals, so with 95 kilotons per annum, followed by monomers and naphtha. And looking only at the monomers and naphtha, nearly 100 kilotons per annum can be used for the production of new polymers, so by utilizing monomer and naphtha. So with this, I think we have a better idea what we can obtain. And now we should have a look on the recycling rates and how do we achieve the quotas. So we already talked about the mandatory recycled content, which needs to be achieved. So I made some calculations based on the amount of packaging waste what is generated, or the packaging what is produced, sorry. And I also calculated the share of PET and other plastics in the packaging. And with this we come to nearly 3 million ton of mandatory recycled content that is needed for the production of new packaging. And if we now compare this with the current recycling rate based on mainly mechanical recycling, so currently we have 10 million tons plastics which is going into the mechanical recycling. But here we should really pay attention. Not every ton of the collected plastic waste for recycling will be recycled. So we assume that only 6 to 7 million tons will be finally recycled with mechanical recycling. And from this, the majority will not be suitable for contact-sensitive applications, simply because contaminations cannot be removed and you cannot really ensure what's in the recyclate. So with this regard, we should put our hope into advanced recycling, because it's capable to provide virgin quality which is allowed for contact-sensitive applications. So keeping now the 3 million tons or 3.9 kilotons of recyclate in mind, what we need, and looking on the timeline. What could we expect from the future? So in this figure, I show you what kind of capacities we could expect in the near future. So these are the announced advanced recycling plants that will be installed. And here you see we could be able to achieve nearly 600 kilotons per annum of virgin quality recycled plastics, but it's more or less still far away from the 2,940 kilotons of mandatory recycled content what we want to cover. So there's a lot of room for improvement in this regard. So to summarize my presentation, I hope I'm not over time. Currently the highest capacities can be reached with thermochemical methods. Most providers which we have identified are pyrolysis technology providers, and the majority of the providers is located in the European Union, and the majority of those are small enterprises, so with 10 to 50 employees. But we have also seen a lot of startups which are popping up. And to summarize regarding the targets, so the targets which have been set up will not be achievable without implementing new recycling technologies. So advanced recycling is necessary to support the mechanical recycling, and the capacities of the technology needs to be further upscaled in order to be able to satisfy the demand. So our projection doesn't show this at the moment. So there's much more to do in order to have higher recycling rates with advanced recycling. And of course, we need clear political framework conditions and additional measures in order to push the whole recycling forward. And this includes the revision of relevant directives, but also the establishment of incentives and investment programs. So, and one or two slides more. If you're interested to gain more insights, so we have published a report on advanced recycling, which will be also updated this year. So in these slides, we are showing at the moment only the report from June 22. So in the next weeks, we will publish our new update. So in the new update includes 30 more company profiles and really an in-depth insight into the worldwide statistics we are still currently working on. And one more slide about our Advanced Recycling Conference, which will take place between 28th to 29th of November. So you are happily invited to attend the conference. We have a full program with 35 speakers from 13 countries. And at the moment, we have more than 230 attendees at the conference, and you are happily invited to attend. So, and with this, I thank you for your attention, and I'm excited for the discussion.
Excellent. Thank you very much, Lars. This was really informative and really gave a good image that it's not a very simple thing just to set up a chemical or plastic recycling in place for example, in the EU. But this really opens up nicely and in an understandable way that what does it mean in practice that there is a large diversity of different kinds of technologies. So thanks for the presentation. We still have a few questions regarding that. You had some questions from online where that it was stated that chemical recycling may not always be sustainable, and then the question after that was, or speculation was, that was this regarding the carbon emissions, or what aspects do you have on that?
Yeah, so I highlighted in my talk that we have currently only small-scale processes. So for a really in-depth in-depth analysis and final conclusion if a process is sustainable, you need to have large-scale processes in order to have a stable result. So there are some first trials to analyze small-scale processes, to interpolate these results. But of course, in the end, you will definitely need a large-scale process to have a final conclusion. And the topic is very complex because your results will depend on the input quality. So you can have a large variation of the results if you change the quality of input. Of course, you can have higher yields at a certain point. So high quality input often means higher yields and higher qualities. But if this cannot be ensured, of course, then you would have a less sustainable process because you have lower yields and maybe not a good quality in order to have later high quality applications. So because you have that so much variations or potential variations, it's really difficult to have a final conclusion on that. Another thing is also what do I compare if I'm looking at the sustainability? So in the past, we have seen a lot of comparison between mechanical recycling and chemical recycling. The question is this a meaningful comparison to conclude which process is more sustainable? So I don't think that this is a good approach because chemical recycling addresses a completely different feedstock than mechanical recycling, or in other words, the feedstock which is chemically recycled cannot be mechanically recycled. And then in this regard, I don't think that a comparison makes any sense because you have no other option to address the waste stream. So it would be maybe more meaningful to compare a chemical recycling process with incineration, because this could be maybe the only option to process your waste. So there are a lot of possibilities to do your comparison, and as I said, a final decision or a conclusion cannot be made yet. And of course, it always depends on a specific technology. So generalizations are also not meaningful here. Maybe we could have with one provider a very sustainable pyrolysis process, and the next provider would have a less sustainable process. This could also be. So the technical details will have also here a huge impact.
Good, thank you. And also opening up how the sort of dimensions are controversial sometimes. I was gonna ask that what is the comparison of LCA and especially carbon footprint between chemical and mechanical recycling, but you already answered that it's not necessarily meaningful to compare those, so it's like comparing pears and apples. So let's not then do that, but let's take some other question. Well, there are questions that what is your estimation that, knowing the sort of the regulatory environment, that would recycling of plastic be at scale by 2030? A simple but quite wide question, but how would you put it briefly?
To be honest, I find it not that simple, because it really depends what do you mean at scale. So you can discuss a lot about what do we understand at scale. But overall, I think, as I already indicated at the very end of my talk, I think there is a lot of room for improvement. Simply by looking at the overall recycling rates. So these rates have to increase to 55%, as I mentioned in the recycling quotas topic. And then we have, on the other hand, the mandatory recycled content for contact-sensitive packaging. And then we also have, beyond plastic packaging, other recycling quotas that needs to be fulfilled, for instance, in the sector of automotive. And looking at all these topics, I think, there is much more room for improvement, and also by looking at the current recycling numbers. So, and I think in the end, all depends on the political framework conditions that are currently in development, as well as the incentives and investment programs that are definitely additionally needed to upscale the available technologies. And in the picture I showed you at the end, we need to increase the capacities much more. And but it's a good sign to see that the announced capacities are more or less exponentially growing or steadily growing. And this is a good first sign, but this speed needs to be supported and increased by incentives.
Yes, I think that we should have a crystal ball to see that how this very important topic we'll develop, but we don't have it, but we now have your research results. It's really good. Just wanted to still point out that it was amazing when sort of like checking the numbers you presented, that if the collection rate of plastic is currently around 40%, still the actual material recycling still remains only on a level of 12% or something like that. So it would mean that if the collection rate of plastic was 100%, still the utilization rate through mechanical recycling would be only around 30%, 33%. So it's something that opens up the reality quite well. So it's the mechanical recycling still is only a limited solution for this, and chemical recycling is then needed, and there is a lot of work to be done. A lot of money is needed, and also decision making and regulation.
Yeah, so to addressing the collection rate, so I think the collection rate was not that bad. So the numbers I showed, exclusively for plastics, we had a collection rate nearly of 98%. I think it's very performant. But in order to improve the mechanical recycling or the output of mechanical recycling, which is currently not that high than we expect normally, or normally would expect. So in order to increase this, we definitely need improved collection systems so that we have more separated waste streams with higher quality. We need better sorting, and we need a better pre-treatment. And with this together, I think the mechanical recycling numbers, but also the advanced recycling. So as I said, advanced recycling is not a black box where you can throw everything in. So it has also certain requirements, and if you have high expectations on your product output, you also have at the same time higher expectations in the input, and an improved collection system as well as sorting and pre-treatment system will definitely improve the yields, the recycling yields, and also the quality of recycling for every technology which is out there.
Yeah, very good. This all makes sense, and a good insight to really sort of draw the picture that what this all is about. Lars, very much thank you for your presentation and participation in Paptic Open House. It was really a glad and joy to have you online with us. Thank you.
You're welcome. It was a pleasure for me.
Good. Let's be in touch.